join Rutger, Vehicle Dynamics Engineer at the Goodyear Tire and Rubber Company, alongside Guido Tosolin from Applus IDIADA, as they unveil an innovative approach to virtual tire development for electric vehicles. In a rapidly evolving automotive landscape, the need for accelerated product development is paramount. This presentation explores the integration of virtual tire models with real-time vehicle simulations, enabling subjective evaluation and tuning in a driver-in-loop.
Hello, welcome again. So my name is Rutger, and today I'm glad I can co-present with Guido Tosolin from IDIADA. And we will present about this activity, virtual tire development for a new electric vehicle through driver-in-the-loop, which is actually a partnership together with Mahindra, Goodyear, and IDIADA. So the topics for today, we will do a brief introduction of the activity, as well as an introduction in the Mahindra IglesiasVehicle platform. We will spend some time on the virtual development methodology applied for this project. After that, we will go a bit more in detail about the real-time model generation, both on the vehicle model side and on the tire model side. We will discuss the virtual development loops that we had for this activity, and we'll conclude with some validation. So first, a small introduction. So basically, Mahindra approached us to develop basically this new electric vehicle platform, and there were some challenges. So very short or time to market, so there was a short development time, as well as let's say the electric platform, so the requirements for the electric vehicle that we had to develop without, let's say, physical prototype availability. So Mahindra, the role of responsibility of Mahindra is, of course, the performance requirements, the targets they would like to achieve for the ride and handling performance. From Goodyear's side, we were basically responsible for the virtual tire development, as well as the virtual modeling and assessment of the virtual prototypes. And the role and responsibility of IDIADA is developing the platform architecture, as well as the development validation, so both on the driving simulator and with their other virtual evaluation capability. So now I will give the word to Guido, who will introduce the Mahindra IglesiasVehicle platform.
Okay, so the Mahindra IglesiasVehicle platform is a completely new electric platform. It's not the same that was presented yesterday, it's a new one. The project started actually 1.5 years ago, and relatively soon the SOP will be reached, and we have already performed 2 loops of prototype tuning for this platform. So we have both the virtual development, but we also have the validation results to present today. The platform will be applied to 5 different products with all different requirements. We have from family SUVs with 7 seats up to coupe-style SUVs, which have completely different kind of requirements. We have different sizes of batteries, and also we have different powertrain configurations with single and dual motors. So we have a wide range of products, which also means a wide range of requirements and a wide range of different constraints. So here we have highlighted the main ones. So some vehicles will have a relatively high COG because we have high ground clearance for some of the cars, and also high rear axle weight because we have up to 7 seats. At the same time, we have on the other side of the spectrum, we will have some vehicles which has quite a strong requirement in terms of sportive handling because of the body shape and expectations for the customer for this kind of vehicles. And all the cars will need to have quite high range, which brings to the high load of these vehicles. And of course, on the lower side of the slide, you can see also some requirements which are very specific to the market, because the market needs to work properly on road profiles which are very challenging, roads which are very complicated to deal with. And at the same time, we need to have a very plush ride comfort. It's a very specific requirement for the Indian customer to have a very plush ride comfort for all the products. So of all these requirements, at complete vehicle level, we need to be cascaded down to the component level. And of course, one of the most important components here is the tire. So this virtual tire development approach has been one of the key aspects of the complete vehicle development. So talking of this, when you say cascading targets from complete vehicle level to component level, normally we like to do this in the virtual environment. And in this case, we had a very strong challenge for virtual development related with the fact that this was a completely new platform, new kind of suspensions, new technologies introduced, such as semi-active dampers, which were completely new to Mahindra. And we didn't have any mule car to be used because of the development time and also because of the lack of availability of similar vehicles in the Mahindra product line. So all the critical decisions for the platform, including the tire development, had to be taken based on what we have been able to see on the simulator, so testing the virtual prototypes in the driving simulator of IDIADA and on the driving simulator of GOODYEAR. Okay, so I'll hand it over to Rutger for the difficult and technical part.
Let's see. So yeah, a bit more about the development methodology. So I think this is nothing new for everyone here in the room. So a traditional, let's say, approach, as we know for physical development, that the actual prototype vehicles, they are set up with the latest steering, brake, and suspension components. And then as a tire supplier, we basically provide physical prototypes that can be tested subjectively on the proving grounds. This can be quite a lengthy process, as we have to build physical prototypes, also ship them all over the world. Let's say, so logistically, that becomes also quite complicated. So for this activity, we wanted to apply, let's say, a virtual development approach, as Guido already mentioned. Basically, that meant that we set up the driving simulator with basically the latest vehicle component configuration via real-time models. And in addition, let's say we developed virtual tire candidates that professional test drivers could evaluate and perform a complete subjective evaluation in virtual scenarios. So this allowed us to basically iterate in a virtual environment where we could test, let's say, multiple candidates and also narrow down the design pace to understand, let's say, the design direction we wanted to go. And the beauty of this collaboration was as well that both, let's say, IDIADA has a DIM 250 identical to ours, so we could seamlessly basically exchange models and integrate them without, let's say, very complex matters. Then a bit more about the real-time model generation. So on the vehicle model side, so IDIADA has, let's say, extensive capability in basically deriving detailed multimodal models, so for example from atoms, and these are then derived and translated to real-time vehicle model. In this case, we were using VIK real-time environment, and these can be connected to a tire model, where we were using for this activity basically physical tire model from Fraunhofer CD Tire. And then all these elements can be integrated in the driver in the loop simulator, both at IDIADA site, which was used for basically evaluating also the chassis architecture. And on the tire model side, we performed basically the generation of the virtual prototypes. So within Goodyear, we have a long history of developing basically our finite element capability. So here you can see an example of a flat track simulation or lateral slip simulation in finite element, which are basically used as an input to derive our real-time tire models. So in the middle, you can see an example of the correspondence between the finite element data in blue and the actual correspondence of the real-time CD tire model corresponding with this data. So this is used to basically derive several virtual candidates that then are integrated into the driver in the loop and tested by our professional test drivers. The evaluation scenarios we were focusing on for this activity were basically limit handling stability as well as the understeer character. This was performed on a dry handling circuit. We also did steering feel, cornering confidence, and lane change stability, which were performed on a general highway road scenario. And on top of that, we also did basically comfort. We did some, let's say, trials also for comfort assessment, so primary body motion, suspension shake, and impact forces. And these were done at deterministic surfaces as well as a paved surface like a badly maintained road. Then we will go a bit more in detail about the virtual development loops and the strategy we applied. So we had at the start of the project, so we had an initial driving simulator session which was basically used to set the requirements for the OE tire development. So as we had no virtual prototypes at this stage yet, we basically used we performed the benchmarking phase, and we used a reference tire model from our library. And with this, we could basically easily change some tire properties during the driving simulator session to understand the direction for the vehicle dynamics targets. From this activity, we basically concluded that we had to focus a lot basically on the yaw damping as well as the vehicle stability. As Guido mentioned, the vehicle had a characteristic of a dominant rear axle weight as well as a high center of gravity. So we had to work with an all-around fitment, even with equal inflation pressure front and rear. So these were basically really the main challenges for the virtual tire development. Then we had 3 different loops, which basically used the methodology as I just explained, where we basically wanted to identify the best virtual tire candidates that could meet the vehicle dynamic targets for this electric vehicle. And finally, from the virtual development loops, we had selected together with in joint test the best virtual spec that were then selected for basically physical build of these tires for soft tool prototype tuning. So here's some more detail about the different development loops. Of course, as well, the challenge here was that basically the platform architecture was being parallel developed together with the tire. So we had, during the different development loops, also changes in platform architecture, hardpoint definition, etc. So basically the vehicle characteristics were changing quite a bit. So of course in the first loops we were not on target, but we could see a clear improvement, especially we had to focus on the limit handling and the vehicle stability, that these performances were meeting the targets. And finally in the third loop we could meet all the performance targets, which also in the middle you can see let's say the change of tire characteristics of the different development loops and the correspondent subjective ratings evaluated by the test drivers on the driving simulator. So both for steering performance as well as for handling response, we could see a clear improvement throughout the different development loops. So now Guido will also explain a bit about the offline activities that were performed with the vehicle model.
In parallel with the loops on the simulator, we're doing, of course, offline simulations to confirm whether or not there was a good alignment between the objective KPIs that we were able to extract from the offline simulations and the subjective feedback that was provided by the driver. So we performed a number of different open loop simulation scenarios, among which steady state cornering, frequency response, but actually quite a few more. And we were able to see also in this case that there was a good agreement between what one would expect, checking the objective KPIs and the actual feedback that we were receiving from the drivers, also providing extra confidence that the tire development were actually moving in the right direction. So some words on the validation, because since when we started the virtual activities, the vehicle has been finally built, and next week actually we're signing off the second loop of prototypes. So we have already gathered a good number of validation data, so of testing data that we have used to see whether the results obtained during the testing, the simulation phases were actually aligned with what the drivers were perceiving in the real cars. So the validation has occurred at 3 different levels. So we have done, of course, kinematics and compliance testing on the vehicles, on the prototypes. That data has been used to validate the suspension models. Then we have done ride and handling objective testing on the tracks. This has been done in the tracks of Mahindra in India. And then third, we have done also the subjective tuning. So initially, the drivers have tested the vehicles as they were defined in the simulator. And one thing that I think it's quite important to highlight is that the same person who has been tuning the car in the simulator was also available in the proving ground tuning the physical car in the proving ground. So that made it possible for us to really have a proper validation of the vehicle also from a subjective point of view. So here you can see some of the results. So we were quite happy to see that not only on the kinematics and compliance side, that it's normally something that we can match quite well and predict quite well with our models, but also on the complete vehicle level side, especially for handling and primary ride, we were able to achieve a very good level of correlation. And so we were able to predict properly the behavior of the vehicle with the tire models provided by Goodyear throughout the project. Of course, in some aspects of the secondary ride, due to the nature of the model, we were not able to achieve a very high level of correlation, but this was kind of expected and already planned. And more importantly, even though it's not represented in diagrams, the drivers were able to feel really a good agreement between what they've experienced in the simulator in the initial phases and what they've tried in the physical cars in the last weeks. And so this brings us to the conclusions. Okay, the first conclusion is that we have seen a proper improvement and a good progression of the performance in the virtual loops in which the vehicles has been tested, and we were able to finally find a good match between the tire performance and the vehicle performance. And the other good positive thing is that we were able to see a good agreement between the objective KPIs that we have seen on the virtual vehicles and the ones that we have seen on the track, giving confidence that we were actually capable to predict properly the behavior of the track of the vehicle in the real world. And the same thing as also applies to the subjective feeling of the drivers. They were able to really perceive the car as something they already recognized from the tuning on the simulator. And this provides us good confidence that this process can be applied in a very consistent way in many different projects. And we would say that probably this virtual approach is actually probably the only way to go if we really want to make projects in the driving simulators, because one thing that we have seen is that if we don't have a good assumption for the tire and a good tire model with which you can work around in the chassis, then the results will be strongly compromised by this. So of course it's very important for us to have this parallel development on the one side, the vehicle development on the chassis, and then the tire development and the matching between the two. So this brings us to the end of the presentation. I don't know if you have some time for questions, but thank you very much for your attention.